Okay, hello students. Today is August 23rd, and basically we are done. Okay, I'm going to close up some final comments on certain calculations, and I'm going to insist on the evaluation. What can you do? Analyze the results from the calculation of irregular or response of the ship in irregular waves, and that's it. Okay. And then in the second part, I'm going to give you some minutes in order to complete the progress control. Okay, since today is Tuesday, so we're gonna do it by group, and that's it. Okay, so let me share the screen here. Can you see my screen, people?
Yes, doctor.
Okay, so this is it. Let's suppose that want to calculate. Let's put a title. Okay, let's see. If motion in irregular seas. Okay, so what we need is to be able to calculate relative motion. There are two cases which are very interesting. Okay, somebody was asking me this afternoon, so I decided that it would be a good idea if I explain to the whole group. Okay, so let's suppose that we want to analyze two cases. For example, we want to analyze the possibility, right, that because of the motion, the propeller is here, the propeller can come out of the water. Okay, that's a big problem because when the propeller rotates, okay, the water exerts a resistance, right? If, because of the motion of the ship in waves, the propeller comes out of the water, let's suppose the water surface is here, so the blade is rotating in the air. And of course, the density of the air is much, much lower than the density of the water. It's roughly 900 times less dense. So you can imagine that if you are rotating and have a resistance with water, and this suddenly comes to rotate in the air, okay? So the resistance is 900 times smaller. So the propeller suffers a sudden acceleration. And that acceleration means that an extra shear stress on the shaft. But then, as after rotates half of a circle, this blade goes again inside the water. And again, there is an increment in resistance. So it's increment in resistance in rotational velocity, and there's also a sudden reduction in omega. So those changes in torque, meaning that there's going to be a sudden increment in tau, shear stress. And this happens every time one blade comes out of the water and into the air and come back into the water. Okay, so it's a good idea if this to analyze what happens with how frequent this phenomena occurs. Something similar, right? When the ship is oscillating in waves, right? And the bow, the forward end, comes inside the surface of the sea. That means that water is going to come into the deck. Probably there are two things here. One is that since you have an extra weight in a very high position, the kg increases. And not only that, but what you're putting on the deck is liquid. So if you have a slow and small rotation, right, that's going to be a free surface effect. And that also increases the kg. Okay, so what's the best situation? Okay, we receive water on deck, and that water starts flowing down. Okay, there's some special holes on the sides, so the water can come down again into the sea. Okay, so we have to leave enough time so all of this water basically comes out of the deck and back into the sea until we have the next time we have another amount of water coming into on the deck. Okay, but since this is a random process, we need to evaluate that using probability. Okay, how can we evaluate these two probabilities? I'm going to explain that. Okay, so for these two parameters, we need to calculate the relative motion of the ship with the free surface. So we need to calculate the possibility that the propeller comes out of the water. Or, for example, we would like to calculate the possibility that water reaches the deck, the forward end of the deck. Okay, so in both cases, we need to calculate relative motion. Okay, so let's go first with the forward end. Okay, now remember, we want to calculate the row. Okay, so if we have the row, we can combine it with the spectral density of the incoming waves. And with this combination, we can produce the spectral density of the response. The response in this case is the relative motion of the forward end of the ship with respect to the sea surface. Okay, to calculate the row, we need to consider harmonic or regular waves. Okay, so to calculate row, okay, we consider regular. Okay, now here we have the ship. Okay, this is midship. Here, this is X, this is Z, this is a water line. Okay, now in this case, we are going to consider, this is a worst situation, we're going to consider that the waves are coming from the bow, from the forward end. Okay, so we have regular waves. So we have to draw regular waves. Because we are going to consider the calculation of row. So from here till here, this is lambda. And this is Z0. That's the amplitude of the wave. And we are going to consider that this is equal to 1 meter, since we want to calculate the row. So in this case, the relative motion of the of the forward end with respect to the free surface is directly, okay, the route, because that's the amplitude of the response, relative motion, with an incoming wave of unit amplitude. And we're assuming that the incoming wave amplitude is 1. Okay? Now, if we use any program that we want, for example, in your case, MaxSurf, you are going to calculate eta 3, okay, as function of time, and also you are going to calculate eta 5 as function of time. So remember, eta 5 means radians. Okay, now zeta 0, that's the amplitude, will produce this surface in green. Let me put this in here. Okay, so we have this. This is zeta 0 cosine of kx minus omega t. Okay, that's what we studied in chapter 4 when we review it. The excitation from the waves because of the beam waves. Okay. So you have to review that, and that depends, people. We have to be very careful. This depends on the reference system employed by the program. Okay. So this is typical of the program that I employ, which is SCORS. But in your case, it's MaxSurf. So you have to look it up in MaxSurf. I'm just going to assume that this is correct. Okay, now, what do we do here? We evaluate this motion in this point. And this point is located at x equal L over 2. So this is for the forward end. This is what we are calculating for the forward end. X is equal to plus L over 2. If you were to calculate the relative motion on the aft end, of course, X will be minus L over 2. Okay, now, this is the motion, the vertical motion of the wave, regular wave, in a point which is located at X equal L over 2. So you go up and down, up and down. Now, what will be the relative motion? Okay, so the relative motion, I'm going to call it W, and I put it F because it's the forward end. So that's going to be the difference between the motion, the vertical motion of the forward end. What is that? That is equal to eta 3 minus L over 2 times eta 5. That's the relative motion. I'm sorry, that's the vertical motion of the forward end. And now we have to take the difference because we want to see the relative motion. So we go and take the difference with this thing here. So it's going to be minus Z0 or e to the I cosine, I'm sorry, kx minus omega t. Instead of x, I'm going to use the position. In this case, the position is also x over 2. That's the relative motion. So for zeta equal to 0, okay, you calculate eta 3. Remember, eta 3 is going to be an amplitude, okay, and e to the I omega t and a phase. Zeta 3 and theta 3, you have to take it from the response, from the results of the Maxsurf computer program. Similarly for eta 5. Okay, so you have eta 3, eta 5, and the elevation of the surface. Those three are harmonic functions. So for each one of them, you have amplitude and phase shift. After you have calculated that, you could get the amplitude. If you do this calculation for unit amplitude of the incoming waves, this amplitude of W sub F will be directly the RAW. Is there any questions about these people?
Doctor, you say that this apply in propellers. When you have
right now, I'm explaining for the possibility of having water on deck.
Oh yeah, doctor.
I will explain that in a minute. Okay. So if you take zeta 0 and equal to 1 meter and calculate that, and use that to calculate heave pitch, okay? And also you replace that zeta 0 equal to 1 meter here. Directly, the amplitude of that is the RAW, because that's the response. In this case, the response is the relative motion between the bow, the forward end, and the wave elevation. Okay? Are we clear? If we're clear, now let's, in a very similar way, we can explain for the other case. So for the second case, so we can say is the aft end relative motion with respect to sea surface. Okay, so we're going to have the same situation. We're going to have the ship here. Here I have midship. I have X like this. This is Z. I have eta 3. I have eta 5. And since I'm going to calculate the RAW, I have to consider a regular wave. So from here to here, this is lambda. Okay, this is zeta 0, and I'm going to take it 1 meter. So everything that I calculate corresponds to the response for a wave amplitude of 1. By definition, that's RAW directly. The only difference now is what? Is that we want to calculate the relative motion on the aft. That's the only difference. So what we need to be careful is with the position to specify the aft end. X is equal to minus L over 2. Okay, so we do. This is the relative motion of the aft end. This is the A here. Is equal to what? Eta 3 minus L over 2 eta 5. Because this minus is this one here. And then we go minus zeta 0 e to the I omega t minus k times minus L over 2. Okay, so we have to specify that the relative motion that we're calculating now is on the aft end. So in this way, since we are taking directly the amplitude as 1 meter for the wave, incoming wave, directly the amplitude of this relative motion is the rho. But in this case, in this second case, it's the rho of the relative motion of the aft end with respect to the sea surface. We can calculate now, okay, spectral density of the response. So the spectral density of the response is going to be equal to, do you remember what's the evaluation, how to evaluate this spectral density of the response? Anybody? Spectral density of the response equal to?
The spectral density of the waves time the rho square.
Exactly. Yeah. So it's this. That. So we want to analyze the relative motion between the forward end. We use the rho that we deduced in the first page. We want to analyze the relative motion of the aft end. In this case, we use this W sub A amplitude. So we can calculate both. Now, for any case, forward or aft, we can integrate the area below this function. So integrating we get sigma squared of the response. Now, what we can do now is we are going to assume that the maxima, the amplitudes, the maxima of this motion could be expressed statistically with the Rayleigh PDF. So with that, we could evaluate the probability that we exceed certain values. That's the next step. Okay, so in the first case, for example, we want to evaluate the possibility having water on the forward end of the ship. So what we need to do here is just to, this is our ship. This is static equilibrium. And here, this is a forward end. So here we have this distance, this vertical distance. This is a freeboard in the forward end. So what we need to evaluate is the probability that the relative motion between the hull, the ship hull, the forward end, and the wave elevation exceeds this value. If this value is exceeded, that means that you have water on deck. Because the relative motion is so large that you can have water on deck. So the probability water on deck is equal to the integral of the freeboard of the forward end until infinity, that the probability density function of the Rayleigh which depends on sigma squared. And this. And Miss Sayo was showing me this afternoon that she found some values, recommended values for this probability. That means that if this probability that you calculate for your ship is larger than this recommended value, that means that your ship is getting water too often on the deck. So probably in that case, what you need to do is to increase the freeboard on the deck. Another thing that you could do is you could try to see if moving some weights aft, you can increase the freeboard on the forward end. And in this way, it is possible that you can solve the problem. Okay. Another thing that we could do also is to calculate the probability that we have the propeller out of the water. It's what we call the propeller race. Okay. And we can do something similar. The probability that propeller races. Now, what we have to do now, let me draw this with a much larger scale in the vertical direction. You will see why. This is the water line. Here we have the propeller. And in this case, what we have to do, for example, that depends on the author, but one of the common parameters that we consider is the depth of the water at the center of the propeller. So let's call this H sub P. Okay. More or less, we could assume that the propeller is located more or less L/2 aft. Again, if the relative motion between the aft end of the ship and the free surface is larger than this HP, that means that the propeller or the center of the propeller comes out of the water. If that probability is very large, that means that quite often this is happening. You have very often you have propeller racing, and probably the shaft will suffer or the propulsion system will suffer. Now, I don't have a lovable value for that probability. That's when you have to look for in the literature. The literature will tell you, for example, what is a recommended value for this probability. Okay, that means that if you are above that value, probably your propeller, when you start oscillating, your propeller will come out of the water very often. And the propulsion system, it's possible that starts suffering some damages. Okay, so again, the probability of propeller racing is the integral from H sub P until infinity, the Rayleigh distribution using the sigma square. This is from the forward relative motion. This is for the aft relative motion. Easy. Are we clear, people? Are we clear? Do we have any questions about this? No? Yes, I need an answer. Would you please turn on your cameras, please, people, because I need to see your faces. I need to see that you are here. Okay, so are we clear, people? Do we have any questions about this?
It's clear,
No?
doctor.
Okay. So if we're clear, then we're going to have, okay, this is a nice parameter to calculate, right? Especially for fishing vessels, since they are going to work. See, fishing vessel, it's a nice example. Why? Because they have to work, for example, tuna fishing vessel. They operate, for example, they depart from Rosorja or Malta, and they navigate towards the west, I'm sorry, to the left. 3-4 days. So you are not working in coastal waters. And still, for example, a 60-meter long ship, fishing vessel, is not such a large vessel. So they operate in open water. They are ocean vehicles, and still they are not so large. So the possibility of moving a lot, it's there. So these are very nice parameters in order to evaluate the response of the ship in waves. Okay, so if you want to do the calculation, this is what you can calculate. I was suggesting, Ms. Sayo, she asked me about this. I was suggesting that what you can do is this, okay? I understand there are 2 or 3. I think there is another group which is not in this class, which is also doing the design for a ship fishing vessel. What you can do is you can share the results. And you can plot a table with the 3 different designs, with different sizes. And you can calculate these parameters, and you can compare. You can see if there is a large difference. Maybe it is possible because of the design. And this is something that we would like to learn. Okay, one characteristic of the design helps you to reduce motion of the ship in waves. Okay, but if you want to do this, the problem is that if you want to compare, of course, the conditions has to be the same. So, for example, everybody calculates the response of the ship in waves coming from the forward end. Okay, maximum speed, several loading conditions, and then you can compare. So talk to you can do even this comparison with different ships. It would be very nice. See, everybody, for example, calculates a certain parameter, right? So you can share this information and summarize in a table. For example, you can present these values according to the length of the ship. Now, you have to be very careful because these are different ships. So the lines are different. So you cannot compare directly one to another. But it would be very nice to see how these parameters change when you go increasing the size of the ship. Those are just ideas. You will see if that makes sense or not. Okay, people, we're going to take a break here for 5-minute break. And when we return, we're going to do the progress control. Okay.